let's make a little cell. Let's actually make a kind of a complicated cell compared to what we've done before. First of all, let's start with a power supply because we want to manipulate our cell potentials away from the equilibrium point. So in order to do that, we have to put power into the system, not let it sit at this normal potential. Power supply, let's make it have a negative and positive terminals. What we can do is we can put in an ammeter again, and we can put in a way to adjust the potential of the power supply. Again, we can do that by using a variable resistor, and by using a little tap on that variable resistor, we can adjust the potential to whatever we desire. So this is our variable resistor again. Let's put in a system of a copper wire that's connected to a thallium electrode in a solution of thallium nitrate. And we have a porous membrane again, might be a glass frit or an agar plug, something like that. We can put in now a KCl saturated solution with calomel. Okay. And mercury and copper. So here's our SCE electrode. So often we can draw this out directly, but often we'll just abbreviate it as SCE. But just remember, so we've got our SCE, and now we've got our sort of electrode of interest would be this thallium ion would be the system we're really interested in. We can actually calculate the potential of that system. And we see that the reduction of thallium to thallium metal has a E0 of minus 0.336, and the SCE would have a E0 of plus 0.242 volts. And since this is actually an oxidation, because we've got that as the anode, we would flip that potential around and we find that the E cell would be equal to plus 0.336 plus 0.242 equal to 0.578 volts. So in other words, if we did not do anything to the system and we just put the system together and we used a voltmeter that didn't allow any current to flow across those terminals and measure the potential, we would find the potential of 0.578 volts on the system. And that would be in the spontaneous direction. In other words, if we did hook a wire up, the thallium would decompose to thallium ions, and we would get a net reduction of the calomel to mercury to drive that reaction. So what happens? Well, suppose we apply various potentials on our power supply. What happens if we apply exactly 0.578 volts on our power supply? Well, in that case, we would have the power supply make our cell go from a spontaneous system to one in which we've got no potential difference between the terminals. In that case, the current would have to be zero because we would have exactly what we'd have for a system that would not occur spontaneously. So if we apply 0.578 with our power supply, the current would be zero. Can everybody see that? If we apply it, if we make the potential of our cell by external means equal to zero, there is no driving force for that reaction, and so that reaction will not occur. Current must be zero. Okay, I want to keep that up there a little bit.
You mentioned using a voltmeter.
Right.
But that's potentially not truly applying use power.
Yeah, initially we can measure with a voltmeter before we've applied any power to it. And as long as we don't have a wire connecting these 2 points so that current can flow through that circuit in this direction, we would not let the circuit go. So in fact, if we just measure that potential, then there would be 0.578 volts of driving force for that reaction to go. But it's not allowed to go at that point. But if we crank our power supply up to a certain potential, so we can actually balance that potential out. We've bucked out that potential, if is the way we would say it, and we can get so that there's no driving force anymore, and so the potential across the terminals is 0. Now, what happens if we apply E applied is less than 0.578? In other words, what's less negative? So we get an oxidative current flow. In other words, we now allow the thallium reaction to occur at some appreciable rate by applying just a little bit less. Now, if we apply just a little bit less potential, maybe we can expect that the rate would be slower than if we applied a little bit more potential, a greater difference in potential. So if we go from, say, 1 millivolt less than 0.578 to, say, 10 millivolts less than 0.578, we might expect the difference in the amount of current that flows. In fact, that's true. And if E applied is greater than 0.578, now we can get a reductive current flow. And this would be anodic, so-called anodic current. This would be a cathodic current flow. The question we want to ask ourselves is, if we apply, say, some arbitrary potential, let's say 0.65 volts, what current flows? And that's really what we're interested in knowing, isn't it? If we apply different amounts of potential, how can we relate the potential difference on the terminals to the current that will flow eventually in our system? That's really what we want to know. So how do we figure that out? Well, first of all, to figure that out, let's try to think about what the current flow actually means. Remember that current in our system is the flow of electrons across that interface. It's a Faradaic current, so we're actually putting electrons from the interface to species in solution, or from the species in solution through the interface. So current is actually flowing as electrons. And that electron transfer at the interface is a chemical change. So the rate of current flow is actually the same as saying, by having a large amount of current flow, it's the same as saying as having a large amount of chemical change. So current flow and amount of chemical change are directly related. So current is actually the rate of the flow of charge versus time. Higher the amount of current we've got, the more charge is actually flowing versus time. Current is in units of amperes, and it's actually a derived unit, which is really just the derivative of the charge flow with time. So current is dq dt, and that would be coulombs per second. So current is not, actually current I think is a fundamental unit, I'm not sure. Anyway, so you would think about the rate of current flow is actually the rate of charge flow versus time. Now Faraday was very interested in this sort of thing, and he was the first to basically stipulate the following, that he said the amount of charge that flows divided by N and F is equal to the amount of moles electrolyzed. So N is moles of material electrolyzed. So Q again is charge. N is the number of electrons in the system. In other words, if we have a system where it takes 2 electrons to do that chemical change, rather than 1 electron to do that chemical change per atom or molecule, then N would be 2 or 1. We'll see that later. F is the Faraday constant. Of course, he didn't call it the Faraday, but later we did in honor of him. And that refers to the, it's a conversion unit that changes coulombs to moles. So Faraday constant has units of coulombs per mole. So taking the Faraday's law, which says that the amount of charge that's flowing in the system is directly related to the amount of chemical change that is occurring, we can come up with a velocity of our rate of the reaction. And so we can say the rate of the reaction, for example, in moles per second. Okay, that's the velocity or the rate of the reaction is equal to the rate of change of the number of moles versus time, dN dt, and that's equal to current over NF. I've skipped derivation, but you can see by using this equation you can quickly arrive at that particular case. So the rate of the reaction is directly related to the current flow divided through by NF. So just simply by monitoring current flow, we can get rates of chemical reaction and the rate of chemical change per second. Okay. Now this, of course, refers to heterogeneous reactions. In other words, ones that are occurring as a process of current electron transfer at the interface, and not necessarily referring to homogeneous reactions that occur outside the electrode interface. We also usually use the rate in sometimes a different way. We use sometimes in the moles per second times square centimeters, whoops, to give us this sort of equation, I over NFA, and that would be sometimes written as J over NF, where this would be a term called current density. The higher the current density would just be a current that's normalized for the size of the electrode. So we'd often want to compare. It shouldn't really make any difference whether we have a large electrode or a small electrode, and often it doesn't. So the amount of current flow really needs to be normalized by the area of the electrode. So we're going to use current and potential to give us information about electrode reactions. Because as you see, by changing the potential, we can make current flow, and by monitoring the current flow, we can actually get information about how fast reactions occur. Let's think about our two situations as before. We have two types of current potential curves. We call these IE curves, or current potential curves. One type where we have what they call the ideal polarized electrode. Let's draw it like this. And where we have no current flow, no matter what potential we apply to our electrode. And then we have the other type of electrode, which they would call the ideal non-polarizable electrode. So what's that tell you about the rate of the reaction? The ideal polarized electrode, that means that no matter what potential we apply to the system, we can't get any reaction to occur. So basically the rate of chemical reaction at that system is zero. No matter what we do, we can't get electron transfer to occur to cause chemical change. Whereas in the ideal non-polarized electrode, or alternately might call it a depolarized electrode, there is, no matter what potential we apply, we get large amounts of current flowing out of the system. And so that suggests a very facile electron transfer interface where even small amounts of potential can cause very large rates of chemical reactions at the surface. And so there's actually some old-fashioned terminology that comes along with this. When we add a solution, a species to the solution, that makes the electrode act in this non-polarizable way, we call it a depolarizer. In other words, adding something to the solution that makes current flow at the electrode to make it non-polarizable is a depolarizer, and that's a kind of old-fashioned term. But you'll see it often as somebody, I've added this amount of depolarizer to my system, and so on. And you can see how we could take a non-ideally polarized electrode, adding some species to it, then because of that species having a very rapid electron transfer process at the interface, can convert it to a non-polarizable electrode. Of course, these are two opposite ends, and real electrodes are in between those 2 points. Just like we'd never see an actual ideal polarized electrode, we can't ever see an ideal non-polarized electrode. Now, if we look at a non-polarizable electrode, the potential where the current goes through zero on this system would be the equilibrium potential. Now, I've got that as the cross there, but that doesn't necessarily mean that's the case. You could have a E at any other point on the system, and that would be the equilibrium potential. Now, the larger we try to, anytime we get a shift away from that equilibrium potential, we call that shift away from the equilibrium potential an overpotential. And we use the Greek letter eta to indicate an overpotential. And so eta is equal to E minus E equilibrium. So if we have a system that is acting like a non-polarizable electrode, but not a very good one, we might see a curve that instead of this one looks something like this, where there is a region where the current is close to zero, but at that point we may be at equilibrium, we don't see a significant current flow. So we would call that shift away from the equilibrium potential eta. Okay, the overpotential, and that is called the overpotential. It's the amount of potential over what is normally, what would thermodynamically be required to get the reaction to occur. So we're always going to have some sort of an overpotential for the reaction to occur. What might be those overpotentials be? Well, let's think of a chemical system in an electrochemical system. Now, an electrochemical system that we might consider would be something like this. Here's our electrode. And at that electrode, we can do a couple of different things. We can make electrons transfer in and out of the interface at the interface as long as we have some species to transfer those electrons to. So if we have a molecule that's stuck on the electrode, that's absorbed onto the electrode surface, we can take an electron away from it and make it oxidized, or we can put an electron on it and make it reduced. So we can cause that reaction to change back and forth. We can also think about the fact that a molecule, to be adsorbed on the surface, has to undergo an absorption-desorption equilibrium process and be present at close to the electrode surface as a non-adsorbed or non-adsorbed species. We can also think about the fact that a molecule may undergo a chemical reaction. That may be perhaps due to the fact that we've added a electron to that system, and that makes it unstable. And then we can think about the fact that in order to get to the electrode surface, we have to actually, I shouldn't have drawn that straight line, but we actually have to undergo a significant amount of mass transfer. So this would be sort of the interface region. And this would be what we call a bulk solution potential outside the region. That interface region might be a few 100 nanometers or less. So in this region, we've got all kinds of interesting processes that must be made to happen to get that electron transfer to occur. So all of these systems, all of these parts can lead to an overpotential. In other words, we need some sort of extra amount of energy, extra amount of potential to get that reaction to occur. And so, for example, we might need some more potential to get, there is actually an energy barrier to cross to get the molecule to be adsorbed and desorbed. That would add to the overpotential. There is an energetic process to do that chemical reaction that has an overpotential thing. We also have to have some energy to get that molecule to the interfacial region. That also adds an overpotential to the system. A lot of paper. So we can think about our overpotential as being a couple of different things, actually three, that we're going to consider right now. N could be equal to mass transfer. Let's put this back up here. Okay, so this would be a mass transfer process. So that would be eta mt. Also could be due to electron transfer. Eta ET. And it can be due to a chemical reaction. And I use RXN there. In other words, each of these processes can make the potential shift away from the equilibrium potential. Some old-fashioned terms for these things are called concentration polarization. In other words, whenever we have open potential, we have, according to the old-fashioned lingo, we've got a polarized electrode. It's shifted away from the situation where we can't, we've actually been able to apply a little bit of potential to it. And that refers to the fact that by varying the mass transfer rate, we can change the polarization amount. This also is referred to as charge transfer over potential, or activation polarization. In other words, not all systems undergo electron transfer easily. There might be kinetic barriers for that reaction, so we need to apply extra amounts of energy to get that reaction to go, and that would be a charge transfer over potential in the old-fashioned terms. Also activation polarization. An old-fashioned term for that would be the chemical reaction polarization. And in fact, we can kind of think of this in this particular way. We can think of all of those systems as having a little resistor effect. Every little effect in that system adds to the overall potential drop in the system, and we have to consider all of those. And we might think about these resistors as mass transfer resistors, the charge transfer resistors, and the reaction resistance. But they're not really resistances. They're in fact nonlinear functions of potential, and so we can't really think of them as real resistances. But under certain conditions, they actually act somewhat like resistors, and so that's where that terminology arose. In other words, each time we have any of these effects to consider, we have to consider the fact that they will add a little bit of extra amount of energy that we need to apply to the system, and that little bit extra energy is called the overpotential. All right. Now,